All right, today we're jumping into a huge one. I mean, maybe the biggest question there is. What is everything, really, made of? And I gotta tell you, the answer is gonna completely change how you see the world.
So let's start with a question. Just look around you for a second. The chair you're sitting on, maybe the desk in front of you, even your own hand. Feels pretty solid, right? I mean, of course it does. Well, what if I told you that all of that stuff is, get this, 99.9999% empty space? Sounds absolutely crazy, I know, but it's true. So how is that even possible? Well, the answer isn't just some boring fact. It's more like a detective story, a real-life scientific thriller. It's a story packed with brilliant minds, totally shocking experiments, and ideas that just shattered everything we thought we knew about reality. And today, we're going to follow the clues. Okay, so our story kicks off a couple hundred years ago. It starts with this really simple but powerful idea from a guy named John Dalton. He's the one who gave us the first real scientific picture of what an atom is. Dalton basically said that everything, the air we breathe, the ground we walk on, is all made of these super tiny fundamental particles. He called them atoms, which comes from the Greek word atomos. And you know what that means? It means uncuttable, indivisible. The absolute, final, smallest thing you can get.
And his theory was it was beautiful in its simplicity. He pictured atoms as these tiny, solid, indestructible little balls, kind of like microscopic billiard balls. All the gold atoms were exactly the same, all the oxygen atoms were exactly the same. But a gold atom was totally different from an oxygen one. And the key thing was you couldn't break them. They were the end of the line. And for 100 years or so, pretty much everyone bought into this. But then, along came a physicist named Ernest Rutherford. And here's the best part. He set up an experiment that he thought was going to prove Dalton's model was right. Instead, what he found blew the whole thing to pieces.
So the plan seemed super straightforward. Rutherford's team was going to fire a stream of these tiny positively charged things called alpha particles, just think of them as little tiny bullets, at a super thin sheet of gold foil. Now, if Dalton was right and atoms are just solid little balls, then these bullets should have just zipped right on through. Easy peasy.
And for the most part, that's exactly what happened. Almost all of the particles just flew straight through the foil. But, and this is a big but, the team noticed something weird. A teeny tiny fraction, just 0.14%, got knocked off course, just a little bit. It wasn't much, but it was a clue. Something was up.
And then that little clue got a whole lot bigger. They discovered that about 1 in every 8,000 of these particles were being deflected by a huge angle. We're talking more than 90 degrees. This just wasn't supposed to happen. It was like these tiny bullets were slamming into something really small, but also incredibly dense and hard.
And get this, in the most shocking cases, some of these particles would hit the foil and bounce almost straight back at them. Rutherford's famous line on this was that it was as incredible as if you fired a cannonball at a piece of tissue paper and it came back and hit you. There was no way around it. The old model of the atom was just wrong.
So, Rutherford had this incredible breakthrough. He figured the atom couldn't be a solid ball. No way. Instead, almost all of its mass and all of its positive charge had to be crammed into this unbelievably tiny, dense point right in the center. He called it the nucleus. And the rest of the atom? Well, that was just vast, empty space, with these little negative electrons floating around somewhere out there. And that right there is the empty space in your chair. But you know how science works. Solving one mystery just creates a new one. And Rutherford's model had a huge, glaring problem. A problem that would take another genius, a guy named Niels Bohr, to solve it. And his solution would pretty much kickstart the entire quantum revolution.
I mean, just think about it for a sec. The nucleus is positive, electrons are negative, opposites attract, right? So based on all the physics they knew back then, those little electrons should be constantly losing energy, spiraling closer and closer to the nucleus until, bam, they crash into it. Every single atom in the universe should collapse on itself in less than a second. But obviously that doesn't happen. The world is still here, so why not?
Well, Bohr came up with this idea that was just completely out there. He suggested that electrons can't just be anywhere. They're locked into specific, stable orbits or energy levels. The best way to think about it is like a ladder. An electron can be on the first step, or the second step, or the third, but it can never, ever be floating in the empty space between the steps.
And this is where we get the famous quantum leap. If an electron absorbs just the right amount of energy, it can instantly jump up to a higher rung on that ladder. And then, when it eventually falls back down to a lower rung, it has to get rid of that extra energy. And how does it do that? It spits it out as a little particle of light, which we call a photon.
Now, this whole ladder idea might sound like just a wild guess, right? But here's the amazing part. Bohr's crazy theory made a prediction about the real world that was so accurate, you could literally see the proof with your own eyes.
See, because every jump down the ladder releases a very specific amount of energy, it creates a photon with a very specific color or wavelength of light. What that means is that every element on the periodic table should have its own unique light signature, like a barcode made of colors. A jump from the third rung to the second gives you one color. A jump from the second to the first gives you a totally different one.
And here is the smoking gun. For years, scientists already knew that if you heat up hydrogen gas, it glows with a few very specific colors. And when Bohr used his new ladder math to calculate the exact colors that hydrogen should give off, his numbers matched the real-world measurements almost perfectly. His theory predicted this exact shade of red light, this specific blue-green, and this precise violet. It was an incredible match.
The theory was just a massive success. I mean, look at this. A key number that was calculated using Bohr's brand new model was a near-perfect match for a value that scientists had measured in labs years before. It was like two completely different puzzle pieces, theory and reality, just snapped together perfectly.
But in science, that's never the end of the story, is it? Every amazing answer just leads to more, and sometimes even harder questions. And as beautiful as Bohr's model was, it wasn't the final answer.
Yeah, the model started to show some cracks. It worked like a charm for hydrogen with its one little electron, but it completely fell apart for bigger atoms. It couldn't explain why some of those colored lines were brighter than others. And maybe the biggest problem of all, it gave us the rules, these special orbits, but it had no explanation for why those were the rules. It was an answer without a reason.
And that, of course, leaves us with one final, absolutely mind-bending question. If electrons aren't little planets zooming around in these neat, tidy orbits, then where in the world are they? Answering that one would force science to throw out the idea of certainty altogether and step into the bizarre world of quantum mechanics, a world of probability clouds and waves. But that, well, that's a story for another time.